these are the objectives for today. And actually, the verifying trig identities come from two sections. The first is fundamental identities, and then the second section is the verifying trig identities. But these actually come from the second section. They actually would have been useful to have known when you did the first section, but they're not presented until the first page of the second section, page 384, if you wanted to look at them. But they kind of give us how we're going to attack these equations. You know, work with one side of the equation at a time. It's often better to work with the more complicated side first. Sometimes that means work on the left. Sometimes that means work on the right. Sometimes it means work on both until they meet in the middle, right? Each time it's a little bit different. You just got to take it for, you know, deal with the problem you've got, right? We will do things like factoring trig expressions, adding fractions. When we add fractions, what has to be true? You need common denominators. So when you add fractions, the simple process of finding common denominator will help us along. Right? This squaring a binomial, there's nothing in these two sections where they ever do that. I'm not quite sure where they think that comes into play, but I didn't see any of that. Everything else on here we're going to do. And then creating a monomial denominator, meaning creating a denominator that just has one term. Sometimes that's important too. Right? We look for opportunities to use fundamental identities. Now, we dealt with these in 4.3, and they look like that. I don't know if you remember. I displayed the same thing, but these are the same. There's more this time, but it starts with these right here. This is page 376. And the first group looks more like definitions, right? Sine is 1 over cosecant. Cosecant is 1 over sine. Tangent is sine over cosine. Cotangent is cosine over sine. We will use those to substitute. Do you remember Pythagorean identities? Sine squared plus cosine squared equals 1. That's like saying a squared plus b squared equals c squared. And then we did this already, right? We showed that if you divide all these terms by sine squared, you get that identity. If you divide all these terms by cosine squared, you get that identity. All three of those are, am I on the right side? Oh, man. Okay, we'll see. All three of those are Pythagorean identities, and we will use those a lot, okay? Those are the ones you use more than anything else. But there's actually some more identities that are fundamental identities, and we use these a lot less. But these top ones, if you remember when we did the graph of sine and cosine, it turned out they're just pi over 2 shifts of each other. Well, you could say that about all the trig functions, right? Sine is a pi over 2 shift of cosine. Tangent is a pi over 2 shift of cotangent. Secant is a pi over 2 shift of cosecant. So that's all that's saying there. And then these are the even and odd identities. If you remember, an even function is a function that is symmetric with respect to the x-axis. And out of our trig functions, the ones that we know so far, the cosine is the one that's symmetric with the y-axis. So that means if I say f of x, right, I get the same thing as I say f of negative x. Doesn't matter if I go positive or negative, you're going to have the same y value. That's what it means to be even. So cosine is an even function. Cosine of negative u equals cosine of u. It doesn't matter if it's negative or positive, the value's the same. And because secant is 1 over the cosine, it's even. All the rest are odd. In an odd function, like the sine of negative u is negative sine of u. So it's like take the negative out, move it to the front. Like I said, we don't use these a lot, but they do come up, and that's what they are. So these are the two even, all the rest are odd. And, you know, the cosine should be, you know, we should be that familiar with the cosine graph to understand that's even. And then to understand its relationship to secant, say, well, then that must be even. And all the rest are odd. So back to this. Oh, that's got to get back to this. Okay. So note which functions are in the final expression that you want. Sines and cosines pair up well. When they say that, sines and cosines pair up well, that means because sine squared plus cosine squared equals 1, right? Or that secants and tangents, tan squared plus 1 equals secant squared, or cosecants and cotangents. They all come from those Pythagorean identities. Right? If anything up here didn't work, then you go to this step. It says, write everything as sines and cosines. Right? Every function could be written in terms of sines and cosines. See what cancels, right? And when in doubt, you know, if you try something and it doesn't work, try something else. These are not the kind of things that there's just one way to do it. All of the answers in the back of the book say answers will vary. There's nothing to look at in the back of the book. So just keep trying. It's the kind of thing, you know, just do everything you can. If it didn't work, try another path. And that'll be your tire drill, right?